In this unit, we put together the reactions we have learned in the past several units and do something useful with it. So this unit is entitled Introduction to Multistep Organic Synthesis. And the goal of this unit is to be able to synthesize large and complex molecules from relatively small and simple starting materials. And this is the task that is done every day by chemists working in the pharmaceutical industry. So let me give you an example that I am very intimately familiar with. And this is a molecule that I call L67. It is a DNA ligase inhibitor that I have actually developed and published the practical synthesis of. So if you look at this molecule compared to most other molecules you've seen so far in this course, this is fairly complex. So it's got a molecular formula of C16H13N4O4Br2 and a molecular weight of 485. So as you can see, there are a lot of functional groups present in this molecule. There's a couple of rings present that are linked together by a chain. So if we wanted to make this molecule, as it turns out, the molecule is made from 4 smaller pieces that are linked together using 3 chemical reactions. And each of the 4 pieces is indicated in a different color in this structure. So the commercially available starting materials that I ended up using for this synthesis, the left-hand fragment in red is 3,5-dibromo-4-methylaniline. Then the green carbons come from ethyl chloroacetate. The orange nitrogens come from hydrazine. And then the right-hand ring is 2-hydroxy-5-nitrobenzaldehyde. So looking at how each of these fragments contributes to the atom count of the final product, the left-hand fragment contributes 7 of the 16 carbon atoms, 1 of the 4 nitrogens, and the 2 bromines. The green fragment contributes 2 of the carbons and 1 of the oxygens. The orange fragment just contributes the 2 nitrogens. And then the blue fragment contributes 7 carbons, 1 nitrogen, and the remaining 3 oxygens. So notice the presence of some extra functional groups in the starting material, specifically in the green piece and in the blue piece, that do not make it into the final product. That is very important because these functional groups actually allow you to do the reactions to bring together the fragments. They are in many cases serving as leaving groups, or at least in the mechanisms of these reactions, they get converted, they either are or get converted into leaving groups. So we will come back and look at this synthesis of this molecule in a lot more detail in the next lesson. I just wanted to give it present it as an overview to motivate this entire topic. But before we get to this molecule, we've got to look at the ground rules for synthesis and look at a simpler case. So the most important ground rule for synthesis is what chemists call retrosynthetic analysis, which put into simpler language means think backwards. So when you're given a target molecule that you need to come up with a synthesis of it, what you have to do is look at that target molecule and mentally dissect it. Once you've mentally dissected it, you can decide which bonds you're able to form using chemical reactions and which reactions you will use to form them. Next thing you need to do is write down the exact starting materials that you will use for each reaction, and then you repeat this strategic process until all of your starting materials fit the constraints of the problem. So in real life, the constraints of the problem is that your starting materials are commercially available in large enough quantities for a low enough price that it is practical to use them as starting materials. There are many compounds that may theoretically be commercially available, but if you could only buy 10 milligrams of them for $100, that's not going to be practical as a starting material for a final product that might be a drug. Okay, so in order to solve synthesis problems, step 2 in the strategy here was decide which bonds you're able to form using chemical reactions and which reactions you will use to form them. So what this means is that you have to have enough reactions in your toolbox to use. And what we have been doing in the previous units on reaction chemistry is learning some reactions to put into our toolbox. So what I want to do right now is take a moment and review the synthetically useful reactions that we know. And this is going to be most, but not every last one of the reactions. And I'm subdividing these reactions into 2 classes. One class are reactions that can be used to increase molecular complexity. So basically to take 2 smaller pieces, put them together, and make a bigger piece. Okay, and in the last unit you learned about 3 of these, the aldol, the Claisen, and the Michael reactions. Indirectly in the last unit, we also learned about alkylation of enolates, which is simply using an enolate as a nucleophile in an SN2 reaction on an alkyl halide. And then in a previous unit, you learned about acetal formation. This doesn't always increase molecular complexity, but it can if you're making something significantly bigger. We learned about imine formation, which is a very common method that's used in the drug industry to increase molecular complexity. And then other reactions that can be used to do so are nucleophilic substitution reactions, sometimes, not always, and acyl transfer reactions, once again, sometimes, but not always. Okay, so the vast majority of the reactions that we've learned about are ones that can increase molecular complexity. The other class of reactions are what are called functional group transformations. And those are reactions that will turn one functional group into another that may be necessary to get the functional group that you need in the final product. It may also be necessary to do one of these reactions to set up a reaction that increases molecular complexity. And we'll see examples of this as we move forward. So some reactions that fall into this category are the oxidation of alcohols to carbonyl compounds, the reduction of carbonyl compounds to alcohols. Basically, any hydrolysis reaction is a functional group transformation. That's taking a bigger molecule and breaking it into smaller pieces, so that's actually decreasing complexity. And then again, some nucleophilic substitution and some acyl transfer reactions are simply changing functional groups without making the overall structure larger or more complex. Okay, so let's put this into practice now. So we've already looked significantly about how we form bonds, so this is just a quick review. We form bonds by reacting a nucleophile with a carbon atom that contains a good leaving group. Okay, so an example of how we can think about this retrosynthetically would be to give you the following problem. And that is to synthesize the following molecule from starting materials containing 3 carbons or less. So as I said, the constraint in the real world is what's commercially available. For the purposes of a first course in organic chemistry, you really don't have any good sense of what is and what is not commercially available, nor are you always solving these problems next to a computer where you can easily look up what is and what is not commercially available. So what I will generally do in the course of these problems is give you the constraint that you need to synthesize this from a molecule of X carbons or less. And we're going to assume that smaller pieces are commercially available and bigger things that they're put together into are not going to be. I realize this is somewhat of an artificial constraint, but it's a constraint that we're going to be working with as we solve these problems. Okay, so given that constraint, how do we hack this problem? Well, there are 6 carbons in the molecule, so given that we're allowed to use 3 carbon fragments, we can carry out this synthesis forming only 1 bond, as long as we bring together 2 3 carbon fragments. So that begs the question now, which bond are we going to form? Well, we're going to form one of the carbon-nitrogen bonds because nitrogen, having a lone pair, is a good nucleophile and it's primed to react with electrophilic carbon. And of course, the reaction that we're going to use to form the CN bond is the simple SN2 reaction, the first truly organic reaction that we actually learned. So there are 2 possible solutions to this particular problem because there are 2 carbon-nitrogen bonds in this molecule. So one solution would be to form the right-hand carbon-nitrogen bond. So we are starting with isopropylamine and reacting that with propylbromide. And the second solution would be to form the left-hand carbon-nitrogen bond. So we have propylamine and we are reacting that with isopropylbromide. Either reaction would work in principle, but if you think back to your detailed knowledge of the SN2 reaction, we know that the SN2 reaction is most efficient with primary alkyl halides. Propylbromide is a primary alkyl halide. Isopropylbromide is a secondary alkyl halide. So given the choice to use a primary alkyl halide or a secondary alkyl halide, we are going to use the primary. Okay, so the first solution I put up that's on the left is the one that is better. And again, I said this on a previous slide, but notice there are functional groups, or at least there is in this case a functional group, namely the bromine, that is present in the starting materials that is not present in the products. And that's always going to be necessary. You can't just form a bond without having leaving groups and nucleophilic atoms present. Okay, so that's the overview of multi-step synthesis. So now in the next lesson, we will go back and look at our L67 synthesis in detail in the context of the strategy and the ground rules that we have developed in the last 2 slides of this lesson.